Good evening everyone, good evening. I welcome you all again to VJEE Enthuse. I hope you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. Yes, hello Janan, hi Ravi. Welcome everyone, welcome to the session. Just let me know in the chat box, give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to everyone or not. Yes. Let me know in the chat box fast. Just give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys or not. Yes? Perfect guys, perfect. All right, wonderful. So just give me a second, we'll be starting. So people, hello Yatin, hello Ashwarya. Welcome everyone, welcome. So as you all must be knowing, it is going to be our fourth session from the chapter Chemical Kinetics, right? And what all things we are going to cover right here in the tonight's discussion. Basically, we are going to do the first order kinetics, right? We'll be seeing the first order reactions. We'll be seeing the integrated rate equation of the first order reactions. We'll be seeing the characteristics of the first order reactions as well. So these are the important, I would say most important topics from the chapter Chemical Kinetics. That is the first order kinetics we are going to discuss in detail, yeah? So before starting the session, for the ones who are new to the channel, let me introduce myself. My name is Wassim Sir, and I'm your chemistry master teacher writer on this VJEE Enthuse channel. Yeah? Perfect guys. The ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which we will be taking live on this VJEE Enthuse channel. Okay? Perfect. All right guys, so these are the things which we are going to cover in the tonight's discussion. We'll be starting with the first order reactions. We'll be deriving the integrated rate equation for the first order reactions. We'll see the graphs which are related to the first order reactions. We'll see the half-life of the first order reactions, and at the same time we'll see some important characteristics of these first order reactions right here. Okay, I'm sure you're ready with your pen and paper. So people, before starting the first order reaction, let's start the session with a small question which was asked in your JEE examination a few years back. Okay, a very simple and ordinary question this is. It looks complicated, but trust me, it's not. Yeah. Okay, see guys, how this sort of a question is to be solved over here. Understand properly what I'm going to say. Okay. Understand each and everything which I'll be writing over here on the screen. Well people, I'm given with a reaction as XA gives YB. This X is the stoichiometric coefficient of A and Y is the stoichiometric coefficient of B, correct? The reaction which is given to me is XA, it gives YB. This is the reaction which is given to me. And I'm given with some parameters as well. I'm given with the equation log of minus dA divided by dt is equal to log of plus dB divided by dt plus what? Plus 0.3. This is something which is given to me. Now understand how this question is to be solved. Basically, as per the question, we are supposed to calculate the value of x and y. As per the question, we are supposed to calculate the value of x and y. Now how to solve this question? Understand. First thing, this is a balanced chemical equation that's given to me. Let me write the differential form of rate for this balanced chemical equation. Okay, I'll say something like this. Rate of reaction will be equal to, if I need to write the rate of reaction with respect to A, where A is the reactant, I'll be starting with a minus sign, 1 divided by stoichiometric coefficient of A, that's X, change in the concentration of A divided by dt, which will be also equal to, with respect to B, which is the product, I'll be starting with positive sign, 1 divided by stoichiometric coefficient of B, that's Y, change in the concentration of B divided by dt. This is your differential rate expression for this balanced chemical equation which is given to me. Yeah. Now we will understand. The condition which is given to me, I can write it like this. Log of minus times change in the concentration of A divided by dt, it is equal to, I must say, log of plus d of B divided by dt, right? Plus what? Plus 0.3. Can I say 0.3 is basically log of 2 to the base 10, right? 0.2 is basically log of 2 to the base 10, as simple as that, right? Okay, log of 2 to the base 10 is basically 0.3, correct? Now, if I'll arrange this equation, I'll be getting something like this: log of minus d of a divided by dt minus d of a divided by dt is equal to log of m plus log of n. That simply means log of m multiplied by n. So it's going to be 2 times change in the concentration of B divided by dt over here. Yeah? Okay. If I take anti-log on both the sides in this equation, what I'll be left with? I'll be left with something as minus times d of a divided by dt. After taking anti-log on both the sides, I'll be left with minus d of a divided by dt is equal to 2 times d of b divided by dt, right? Or I can write this equation as minus 1 divided by 2. If I'll take this 2 as in the denominator right here, it's going to be minus 1 by 2 d of a divided by dt will be equal to d of b divided by dt. As simple as that, right? Okay. Yes. Now people understand. If you compare this equation with this equation, just compare the two equations. On comparing the two equations, I'm just saying one thing. I'm just saying this x has to be equal to what? This x has to be equal to 2, right? And this y over here has to be equal to 1. Okay? If I compare this equation with this equation, on comparing the two equations, you get simply the value of x as 2, and you get the value of y as 1. These were the stoichiometric coefficients over here in this reaction which I was supposed to calculate. Yes, I'm sure you got the concept. Let me know in the chat box if it's clear to everyone so that I can move on. Okay? Yes? Right? Let me know in the chat box if it's clear to everyone. Fast. Let me know. Chaitanya, I have no idea. Is the video lagging? Is the video lagging? Can you let me know? Ravi, this is the English channel. I'm not supposed to talk in Hindi. Praveshini, it's simple. 0.3 is basically log of 2. You have to use a bit of common sense right here. Okay? Perfect, guys. All right. Okay. So let's move on to our actual topic, which we are going to cover right here. That's going to be the first order reactions. Okay? So first thing, what are these first order reactions? Let's try to understand these first order reactions. Okay? First of all, let me tell you, first order reactions are the ones in which rate of the reaction varies linearly with the concentration of reactant. Okay? That reaction in which the rate of reaction varies linearly with the concentration of reactant, that's something which I call as first order reaction. For example, have a look. Let's say I'm taking a reaction as A gives B. Let's say this is a balanced chemical equation whose rate constant is, for example, K. I'm assuming the order of reaction is 1. Okay? I'm assuming the order of reaction is 1. Perfect. Now we will understand few important things over here. See, at time t is equal to 0, when the reaction has not started, at that time, let's assume the concentration of reactant is A0. And at the same time, the concentration of product will be 0 because the reaction has not started yet. Okay? If the reaction has not started yet, that actually means the concentration of product will be 0 at time t is equal to 0, right? When the reaction will start, what is going to happen to the concentration of reactant? The concentration of reactant will be decreasing with time and the concentration of product will be increasing with time. As simple as that. Let's assume at time t, the concentration of reactant left is represented by AT and the concentration of product formed is represented by BT. Okay? Now I'm assuming this is a first order reaction. That means the rate of the reaction will be equal to K multiplied by concentration of reactant raised to the power order, that is 1. This is how I wrote the rate law. For the given reaction A gives B. Okay? As simple as that. Understand properly what I'm going to do. First of all, I know the order of reaction is 1. Therefore, this is how I'll be writing its rate law. right? As per rate law, rate of the reaction is equal to rate constant multiplied by concentration of reactant raised to the power order. As you can see, the rate of reaction is varying linearly with the concentration of reactant. Yes, the rate of reaction is varying linearly with the concentration of reactant. Okay. Now people, I have already assumed this as the balanced chemical equation. If it is a balanced chemical equation, I can say rate of reaction will be equaled. With respect to A, I'll be starting with minus sign, change in the concentration of A divided by dt over here, right? This is how I wrote the differential form of rate. Okay, this is how I wrote the differential form of rate. Yes. So people understand what I'm going to do the next. Understand properly. Okay. See, if I write this equation at time t, at time t, I can say rate of reaction will be equal to rate constant multiplied by, what is the concentration of A at time t? At time t, the concentration of A is 80, so it's going to be 80 raised to the power 1, okay? Similarly, if I'll write this expression over here at time t, I'll say rate of reaction will be equal to minus times d of 80 divided by dt. I wrote this equation at time t as well, okay? Now understand, at time t, this equation is giving me rate of reaction. At the same time, this equation is also giving me the rate of reaction. So both the equations are giving me the rate of reaction at a given time, at a particular time instant. So I can say clearly, whatever rate of reaction you'll be getting from this equation, same will be the rate of reaction you'll be getting from this reaction at time t, okay? So if I equate these two terms over here, what I'll be getting? I'll be writing minus d of 80 divided by dt is equal to what? Is equal to k multiplied by 80, because both the terms are giving me the rate of reaction at time t, okay? Now people understand. If I separate the variables over here, I can simply say like this, d of 80 divided by 80 is equal to minus k dt. I just separated the variables. Since I'm going to derive the integrated rate equation, for the first order reactions. So I'll be integrating on this side as well as I'll be integrating on this side. On the right hand side, I'm integrating with respect to time, and time changes from 0 to t. This is the time interval 0 to t. So lower limit is going to be 0, upper limit is going to be t, okay? And at time t is equal to 0, what is the concentration of reactant? Because on the left hand side, I'm integrating with respect to concentration of reactant. And at time t is equal to 0, what is the concentration of reactant? That's A0. So lower limit is A0. Similarly, at time t, what is the concentration of reactant? That is AT. Okay, as simple as that. Okay. Now people, we are almost done. Understand. We are almost done. See. Integral of d of AT divided by AT. What it's going to be? You all must be knowing integral of dx divided by x. This is what we write as ln of x to the base e. Okay. In the similar way, integral of d of AT divided by AT, I'll be writing ln of AT. Okay. And the limits are going to be A0 to AT. Okay. This is equal to k is the rate constant. I'll take it out. So minus k I'm taking out. Integral of dt means simply t, right? Limits are going to be 0 to t over here. Now put the upper limit, put the lower limit. You'll be getting something as ln of AT minus ln of A0 will be equal to minus times kt, or you'll be writing as ln of AT is equal to ln of A0 minus kt. This is one of the forms of the integrated rate equation for the first order reactions. Okay, this is one of the forms of the integrated rate equation for the first order reactions. Similarly, there are a lot of forms of the first order integrated rate equation. Let's get to know those forms as well. Okay, this is one of the form over here about the integrated rate equation for the first order reactions. Yeah. Now people, let's talk about few more important things. Understand. This is ln of AT. Instead of ln of AT, I can write 2.303 log of AT. I can write it like this is equal to ln of A0. Instead of ln of A0, I can write 2.303 log of A0. Okay, and minus kt I'm writing as such. Yeah. If I divide this equation throughout by 2.303, I'm dividing this equation throughout by 2.303. What I'll be getting? see what I'll be getting over here. On dividing the equation throughout by 2.303, you are getting log of 80 to the base 10 is equal to log of a naught to the base 10 minus k divided by 2.303 multiplied by t. This is one more form of the integrated rate equation for the first order kinetics, okay? For the first order reactions, this is one more form of the integrated rate equation, okay? Now there are few more forms of this integrated rate equation for the first order reactions. You must know all these forms, okay? Let's try to understand those forms as well. Understand properly what I'm going to say. Understand properly what I'm going to say, okay? See guys, understand what I'll be writing. Ln of 80 minus ln of a naught. So ln of m minus ln of n. That's going to be ln of m by n. So it's going to be ln of 80 divided by a naught is equal to minus kt. Okay, I'm simply using normal maths. This is ln of m minus ln of n. That becomes equal to ln of m by n, right? Okay. Now people, if I multiply throughout by minus, it becomes ln of a naught divided by 80. I'm multiplying throughout this equation by minus. After multiplying this equation by minus, you'll be taking the reciprocal, so it's going to be ln of 80 divided by, ln of a naught divided by 80 is equal to k multiplied by t. What is the base of the ln over here? It's e, okay? Can I write something like this? Or wait, let me keep it as such. Cy. Understand, Cy. Let me write it as such. See, the base over here is e. I'll be writing 80 divided by a naught. 80 divided by a naught will be equal to, I'm converting it into exponential form. It's going to be e raised power minus kt. Or I can say 80 is equal to a naught e raised to the power minus kt. This is one more form of the integrated rate equation of the first order reactions. Okay? Right? As simple as that. What is AT basically? AT is the concentration of reactant left at time t. What is A naught? A naught is the initial concentration of reactant. Okay? This is one more form of the integrated rate equation. Now let's try to make few more forms of the integrated rate equation for the first order kinetics. Okay? Let's understand. See. This is ln of AT minus ln of A naught. So instead of ln of AT minus ln of A naught, I can clearly say ln of AT divided by A naught. Ln of AT divided by A naught is equal to what? Is equal to minus kt. This is something which I wrote, okay? If I multiply this equation now with a minus sign, you get something as ln of A naught divided by AT is equal to kt, okay? Or you get the equation as k is equal to 1 divided by t. It's going to be ln of A naught divided by AT. This is one more form of the integrated rate equation for the first order reactions, okay? Similarly, I can convert the same equation into a different form as well. I can say k is equal to, this is ln of A naught by AT. I can say it is 2.303 divided by t. Now it's not going to be ln, it's going to be log of A naught divided by AT. These are few different integrated rate equation forms for the first order reactions. I'm sure it will be clear to everyone. You can just let me know in the chat box, give me some green signal from the chat box so that I'll get to know whether all these integrated rate equation forms for the first order reactions are clear to you or not. Let me know in the chat box so that I can show you some curves based on these first order kinetics, yeah? Okay. Perfect. Hello Yatin, hello Deborah, hi Harshil, hello Danish, hi Priyanshu. Welcome everyone, welcome back. Perfect guys, perfect. All right, yes Harshil, it's a new setup. That's why I am looking on my left, yeah? This is a new setup. That's why I'm looking on my left, because the screen is on my left. Yes? Perfect guys. So let's move on and let's talk about few more interesting things about the first order reactions. Okay? So whatever forms I gave you about the first order kinetics, let me write those forms once again so that we can make some curves related to those first order reactions. First order kinetics. See, the first curve which I'm going to make over here, it's going to be between rate of reaction versus the concentration of reactant. Rate of reaction versus the concentration of reactant. We know for the first order reactions, R is equal to K multiplied by concentration of A raised to the power 1. Okay, this is how we write the rate law for the first order reactions. You all must be knowing it now. I'm plotting rate of reaction along y-axis. I'm plotting concentration of A along x-axis, right? So instead of R, I can write Y. Instead of A, I can write X. So Y is equal to mx, means straight line passing through origin. And what is going to be the slope of this curve? Slope means the value of m, and the value of m over here is equal to k, where k is the rate constant. This is the first curve which I have made for the first order reactions. Yeah. The second curve which I'm going to plot for the first order reactions, what it's going to be? It's going to be ln of AT versus T. Ln of AT versus T. Few minutes back, I gave you one equation, if you remember. That was ln of AT is equal to ln of A naught minus KT. This is the equation which I gave you few minutes back for the first order kinetics. Okay. I'm plotting ln of AT along y-axis. I'm plotting T along x-axis. So instead of ln of AT, over here I'll be writing y. Instead of T, I'll be writing x. So before x, what comes? M comes. What is the sign right here? Minus. Instead of this whole term, I'll be writing c. So y is equal to minus mx plus c. The curve is going to be a straight line with the positive intercept but the negative slope. So slope of this curve is basically equal to minus k. Slope of this curve is equal to minus k. If I talk about this intercept, intercept means the distance from the origin to the point from where the curve starts, which is denoted by c, and c value over here is ln of A naught. So this is the intercept of the curve. This is the intercept of the curve over here. This is one more curve which we have drawn. Okay, let's make one more curve. Let's make one more curve. What is that curve going to be? It's going to be the curve between log of AT versus T. Log of AT versus T. Okay, how will I be making it? Understand. Right now, I'm plotting log of AT along y-axis. I'm plotting time along x-axis. Few minutes back, I gave you one equation. What was that? That was log of AT is equal to log of A naught minus K divided by 2.303 multiplied by T. Okay, this is the equation which we have derived few minutes back. Along y-axis, I'm plotting log of AT. So instead of log of AT, I'm going to write y over here. Instead of T, I need to write x. Okay, so this whole term becomes your slope, which is minus m right here, and this term I'll be calling as intercept c. Y is equal to minus mx plus c, again is a straight line with a negative slope, and the slope of this curve over here is simply equal to minus k divided by 2.303. What about the intercept? Intercept is denoted by c, and c value over here is log of A naught, right? So this is something which I call as intercept, and intercept is right now log of A naught. Okay, these are three important curves which we have made for the first order reactions, right? Let me know in the chat box if everything is clear till here. Hello Rohit. Hello everyone. Hello David. Let me know in the chat box if everything is clear till here so that I can move on to the next one. Let me know fast, yeah? Let me know fast. Perfect guys, perfect. Let's move on and let's talk about a few more important curves, okay? I'm going to plot a curve now between AT versus T. I'm going to plot a curve between AT versus T for the first order reactions. And a few minutes back, I gave you one equation. AT is equal to A naught e raised to the power minus KT. Okay? Understand, I'm plotting AT along y-axis. I'm plotting T along x-axis. So instead of AT, I'll be writing Y is equal to, okay? Y is equal to A naught, I'm writing as such, e raised power minus K, and instead of T, I'm writing X. So this equation resembles with this, right? This equation resembles with this, right? And what is the nature of the curve for y is equal to e raised power minus x? It's exponential decrease curve like this. It's exponential decrease curve. And the curve won't be touching your x-axis. The curve won't be touching your time axis anywhere over here, okay? Yes? Okay, this is exponential decrease curve. I'm sure you all must be knowing this as well, right? I'm sure these curves are clear to you. Let's move on and let's talk about few important things about these first order reactions, okay? Integrated rate equation we have derived. All these curves we have already made for the first order reactions, okay? Now let's talk about something called as half-life of the first order reaction. You can let me know in the chat box if everything is clear till here so that I can move on to the next one. Let me know in the chat box. Let me know in the chat box. Let me know in the chat box if everything is clear till here so that I can move on to the next one. That's what I call as half-life. Let me know fast. Yes. Let me know, give me some green signal from the chat box so that I can move on to something called as half-life of the first order reaction. Okay. Perfect, guys. Perfect. Wonderful. Now, let's get to know what the half-life, how to calculate half-life of the first order reaction. Half-life is something which I have defined in the last session as well when we spoke about zero order reactions. Okay. Surely, Mr. G creation, I'll be making one short series as well. Okay. Right. Surely I'll be doing that. So let's get to know the half-life of the first order reactions. Understand? Let's say I have got the reaction A gives B. Let's assume rate constant of this reaction is K, and I'm assuming the order of reaction is equal to 1. That means the value of N I'm keeping as 1. Order of reaction I'm taking as 1 over here. Okay. Now people, few interesting things, few important things. Let's assume at time t is equal to 0, the concentration of reactant is A0, the concentration of product absolutely is going to be 0, right? Okay. Now people, when the reaction will start, what is going to happen? When the reaction will start, the concentration of reactant will decrease. Can I say there will be a time when the concentration of reactant left will be A0 by 2, and the concentration of reactant left I always represent by AT, right? When the reaction will start, the concentration of reactant will keep on decreasing, and there will be a time when the concentration of reactant left will be A0 by 2. Okay? Yes. And the time at which the time duration in which the concentration of reactant changes from A0 to A0 by 2, that's something which I call as half-life. That's something which I call as half-life, right? So this time interval is what I call as half-life. Okay? Right? As simple as that. Yes. So people, again I'm telling you, the time for the reactants to change the concentration from A0 to A0 by 2 is something which we call as half-life. Yeah. So can I say at T is equal to T half, at T is equal to T half, the concentration of reactant left, which I'm representing by AT, that's basically equal to A0 divided by 2. Okay. What is my integrated rate equation all about? What is my integrated rate equation all about? Few minutes back I told you K is equal to 1 divided by T ln of A0 divided by AT. This was one of the forms of integrated rate equation for the first order kinetics. Okay. Now people, if I'm using this condition into this equation, I'll be getting K is equal to 1 divided by, instead of T I'll be writing T half, it's going to be ln of A0 divided by AT. Instead of AT, I'll be writing A0 divided by 2. A0 gets cancelled out. So you get K is equal to 1 divided by T half. 1 divided by T half, it's going to be ln of 2. Okay? Or you get something as T half is equal to ln of 2 divided by K. Right? This is the expression for the half-life of the first order kinetics, for the first order reaction. And you can write it in different form as well. As you all must be knowing, ln of 2 is nothing. Ln of 2 is 0.693, okay, divided by K. You can use either of the expressions in order to calculate half-life for the first order reaction. Okay. Well, people, if you look at this expression, in this expression, are you seeing any sort of concentration term involved in this expression? You're not seeing any sort of concentration term involved in this expression. Yeah. Can I say half-life of the first order reaction, it's independent of the initial concentration of reactant? Absolutely. Half-life of a first order reaction, it's independent of the initial concentration of reactant. Okay. So if you need to plot a curve right here between half-life of the first order reaction versus initial concentration of reactant, since half-life of the first order reaction does not depend on the initial concentration of reactant, so the curve is going to be a straight line. Okay. Parallel to the concentration of reactant excess over here. Yes, because on changing the concentration of reactant, the half-life of the reaction is not going to change at all. Okay, I'm sure it's clear to every single guy over here. Yeah, this was something which we call as half-life of the reaction. Now there is one more point. That is what we call as completion time. Okay, that's what we call as completion time. Let's talk about the completion time of the first order reaction. Let me tell you, a first order reaction never gets 100% completed. Okay, a first order reaction never gets 100% completed. A first order reaction never undergoes 100% completion. Why? How can we justify this statement? Let's try to understand this. Have a look, guys. Again, I'm taking some first order reaction as A gives B, whose rate constant is K, and the order of reaction is 1. N value is 1. Okay, right? At time t is equal to 0, what is the concentration of reactant? That's A naught. Concentration of product, that's going to be 0, right? That's going to be 0. Understand? Yes, Raju, I'm right now live from Srinagar, Jammu and Kashmir. Yes, exactly. Okay, see guys, look here. At time t is equal to 0, the concentration of reactant is A naught and the concentration of product is 0. Now what is going to happen? When the reaction will start, the concentration of reactant will decrease with time. I'm assuming there will be a time when whole of the reactant would have got converted into the product. So at that time, the concentration of reactant left, which I represent by AT, that is going to be 0. Okay? And the time in which the concentration of reactant changes from A naught to 0, that's something which I call as completion time. That's something which I call as completion time, which we represent by T 100%. So I'm assuming whole of reactant is getting converted into product, right? And the time taken for the reactant to get completely converted into the product, that defines the completion time of the reaction. Okay? So can I say something like this? Understand properly. Can I say at T is equal to T 100% at the completion time of the reaction, there will be concentration of reactant left is going to be 0 because entire reactant would have got converted into the product. Yeah? Okay? Now we will understand. If you use the first order kinetics, K is equal to 2.303 divided by T, it's going to be log of A naught divided by AT. This is the integrated rate equation for the first order reaction. Okay? Or just remove this T over here. Instead of T, you can write K, and instead of this K, you can write T. One and the same thing. If I'll put the given condition into this expression, what do I get? Instead of T, I'll be writing T 100%. That is the completion time of the reaction is equal to 2.303 divided by K. It's going to be log of A naught divided by, instead of AT, I'll have to write 0. Okay? So if over here I'm writing 0, division by 0 becomes infinity. So this whole term, it approaches towards infinity. What it means? This whole term approaches towards infinity. Okay? It simply means time taken to complete 100% of the first order reaction is infinity. Or I can say a first order reaction takes infinite time for the completion. A first order reaction takes infinite time for the completion. Okay? Again, I'm telling you, a first order reaction takes infinite time for the completion. Yeah? We can say that. Or I can clearly say, a first order reaction never undergoes 100% completion. A first order reaction never undergoes complete completion. Yeah? 100% completion, I mean. Okay? Right? Let me know in the chat box if it's clear to everyone. So remember this statement, a first order reaction never undergoes 100% completion. Okay? That is why I made a curve a few minutes back. That was the curve between AT versus T, and the curve started somewhere from here, and it was exponentially decreasing curve. I told you the curve is never going to touch your x-axis. The curve is never going to touch your time axis, right? Because when the curve will touch the time axis, at that point the concentration of reactant becomes 0. And the concentration of reactant never becomes 0 in case of first order reactions, right? Because the first order reaction never undergoes 100% completion. Okay? That's why this curve never touches the time axis. Okay? As simple as that. Let me know in the chat box if everything is clear till here. Let me know fast. Let me know in the chat box if everything is clear till here. Yeah? Darshan, I'm not ignoring. Well, the SRM and VIT both are almost equal, bro. Yeah? Well, I think Shreya sir has already taken a session, comparison between SRM and VIT. You just search that video on YouTube. You'll be getting to know what are the pros and cons of both the institutions. Yeah? You'll be getting to know that. Thank you, Mishani doctors. Perfect. But Arslan is saying, sir, repeat something. Bro, what do you mean by repeat something? Repeat something. Wow. Okay, let's move on. Let's talk about few more interesting things. Let's talk about the degree of dissociation in case of a first order reaction. Let's see how degree of dissociation is calculated in case of the first order reactions. Understand properly how will I be doing it, yeah? So people, in your class 11th equilibrium, you would have discussed something called as degree of dissociation alpha, which is always equal to number of moles of reactants dissociated into the products divided by initial moles of reactants taken. Okay, what is ND? ND means number of moles of reactants dissociated into the products, and Ni, it represents what? It represents the initial moles of reactants taken. Okay, understand what I'll be doing over here. Let's assume I've got a reaction A gives B. It's a balanced chemical equation whose rate constant is K, and I'm assuming the order of the reaction is 1. So this is the first order reaction, yeah? Okay. Let's assume at time t is equal to 0, the initial concentration of reactant is A0, the initial concentration of product will be 0 because the reaction has not started yet. Okay, the reaction has not started yet, right? Now people, at any time t, the concentration of reactant left is represented by AT. We know it, okay? First of all, if you remember, in the first session of kinetics, I told you, what is concentration basically? Concentration is number of moles divided by volume of the system in liters, right? We know it, right? See, this reaction will be taking place in some container, yeah? Let's assume volume of that container is 1 liter. Let's assume volume of that container is 1 liter. So I can say, in case of this case, in which the volume of the system is 1 liter, I'll say concentration of A will be equal to number of moles of A, right? Similarly, concentration of B will be equal to number of moles of B, because the volume of the system I'm taking as 1 liter over here, yeah? So people, these are the concentrations, or you can call them right now as the moles as well. I can say this A0, these are the initial moles of reactants, and AT, these are the moles of reactants which are left at time t, okay? So initially you had A0 moles. Finally, you are left with AT moles. So can you let me know something? Alpha is equal to how many moles of reactants dissociated into the products? Initially, I had A0 moles. Finally, I'm left with AT moles. So A0 minus AT is going to give me what? A0 minus AT is going to give me the number of moles of reactants which are getting converted into the products, yeah? Okay? Yes. Divided by initial moles of reactants, that is A0. Few minutes back I told you one general equation which was AT is equal to A0 e raised to the power minus KT divided by what? Divided by A0. If you take A0 common in the numerator and A0 is already in the denominator, so you can cancel the two, you'll be getting alpha as 1 minus e raised to the power minus KT. So this is how you calculate the degree of dissociation for the first order reactions, okay? This is how you calculate degree of dissociation for the first order reactions. Similarly, if you talk about the zero order reactions, how do we calculate degree of dissociation for zero order reactions? It's again going to be same. Alpha is equal to A0 minus AT divided by A0. But right now I'm talking about the zero order reactions. And in case of zero order reactions, we know AT is nothing. AT is A0 minus KT as per the integrated rate equation of the zero order reactions are concerned, divided by A0. Okay? Yes. So you get from here alpha is equal to KT divided by A0. This is the degree of dissociation for the zero order reactions, and this is the degree of dissociation for the first order reactions. Okay? So you sometimes the question gets asked simply, which of the following expression is correct for the degree of dissociation for a zero order or first order reactions? And the expressions for the degree of dissociation for zero order and first order are mentioned over here. Yes? Now people understand. Understand properly. This is for zero order reaction. This is for first order reaction. In this expression, are you seeing any concentration term involved? Is there anything in the expression as concentration of reactant or concentration of product? No way. Can I say degree of dissociation of the first order reaction, it's independent of the initial concentration of reactants? Because in this expression, you're not seeing any concentration term involved, right? So you can clearly say degree of dissociation of the first order reaction, it's independent of the initial concentration of reactant. But if you talk about the zero order reactions, alpha is inversely proportional to A0, and A0 is something which I call as initial concentration of reactant. Yes. So I can say in case of zero order reaction, alpha depends on the initial concentration of the reactant. But in case of first order reactions, alpha does not depend on the initial concentration of reactants. Yes? Okay? A very, very simple question this was. Yeah? Okay? So I'm sure this is again clear to you. You are clear with the degree of dissociation. So note these two statements. These were asked somewhere in your JEE as well. I don't remember the year. Okay? So degree of dissociation alpha for a zero order reaction, it depends on A naught. Okay, whereas degree of dissociation for a first order reaction, it does not depend on the initial concentration of reactant. Very, very simple again. Okay, now people, let's move on and let's talk about the time taken to complete X% of the first order reaction. How much time it takes, for example, to complete 20% of the first order reaction, how much time it takes to complete 80% of the first order reaction, how much time it takes, for example, to complete 25% of the first order reaction. How do we check that? How do we do that? Okay. Understand properly. After that, I'll be giving you the idea about this expression over here. I mean, this statement over here, but after deriving certain things. Understand? Let's assume I've got the reaction as A gives B, and I'm assuming this is a first order reaction whose rate constant is K. The order of reaction is 1. The order of reaction is 1. Yeah? Okay. Vignesh, I'm doing great. How are you? All right. See, guys. At time t is equal to 0, for example, the initial concentration of reactant is A naught. The initial concentration of product will be 0 because the reaction has not started yet. Yeah? Okay, we know it. Now, for example, let's assume X% of reaction is getting completed. Let's assume X% of reaction is getting completed. What does that mean? That simply means X% of the reactant is getting converted into the products. Okay? And time taken for the reaction to complete its X%, time taken for the reaction to complete its X%, that's something which I'm representing by Tx%, right? Time taken for the reaction to complete its X%, time taken for the X% of the reactants to get converted into products is represented by Tx%, okay? So people, if right now X% of the reactant has got converted into products, so what is the percentage of reactant left at this time? I'll say the percentage of reactant, the concentration of reactant left is going to be 100. Just a second. See guys, A naught is the initial concentration of reactant. Okay, A naught is the initial concentration of reactant. So the concentration of reactant left when X% of the reaction is completed, how much that's going to be? That's going to be initial concentration, which was A naught, minus X% of the reaction is getting completed, right? Minus X% of the reaction is getting completed. X% of A naught is getting converted into products. So this much of amount of reactant is left right now. Okay? Understand once more. Initially, I had the initial concentration of reactant as A naught. Now X% of reactant is getting converted into products. So what is the concentration of reactant left at this time? Initially, I had A naught, the concentration of reactant. How much concentration of reactant is getting converted into products? This much of concentration of reactant is getting converted into products. So what is the concentration of reactant left at time t? It's going to be A naught minus X% of A naught. So can I write it as A naught minus X divided by 100 multiplied by A naught? I can write it like this. This is basically your AT. Yeah? As simple as that. Right? Right? Let me know in the chat box if it is clear till here. Let me know fast if everything is clear till here. Let me know fast. Let me know fast if everything is clear till here. Yeah? Okay. Now we will understand. This is the value of AT. This is the value of concentration of reactant left at time t is equal to X%. Yeah? Now if I use the integrated rate equation, what was my integrated rate equation all about? I used to write T is equal to 2.303 divided by K. It used to be log of A naught divided by AT. Okay. Now if I put this condition into this equation, instead of T, I'll be writing Tx%. That means time taken to complete X% of the first order reaction is equal to 2.303 divided by K. It's going to be log of A naught divided by AT. What is AT? AT is A naught minus X by 100 into A naught. Okay, if I take A naught as common, what do I get? I get 1 minus X divided by 100. Okay, this is something which I got. Can I say A naught got cancelled? A naught got absolutely cancelled. So you got to know time taken to complete X% of the first order reaction. It's always going to be 2.303 divided by K. And right here, I'll be writing log of, it's going to be 100 divided by 100 minus X. Okay, so this is how we calculate the time taken to complete X% of the first order reaction. Okay, this is how we calculate the time taken to complete X% of the first order reaction. So if you need to calculate the time taken to complete 25% of the reaction, you will simply put the value of X as 25. You will simply put the value of X as 25. If you need to check how much time it takes for the reaction to complete its 45%, you will simply take the value of X as 45%. As simple as that. Okay, right? So people understand. In this expression, are you seeing anywhere the term A naught? Is there any term A naught included in this expression? In this expression, there is no term A naught included as such. Can I say time taken to complete a certain fraction of first order reaction? Time taken to complete a certain percentage of a first order reaction that's independent of the initial concentration of reactants. Okay, time taken to complete a certain fraction, or you can say time taken to complete a certain percentage of a first order reaction, it's independent of the initial concentration of reactants. Okay, why am I giving you this statement? Why am I giving you this statement? There's a reason for it. Okay, understand why am I giving you this statement? See, for example, I have got the reaction as A gives B. I've got the reaction as A gives B. Again, I'm going to write the same reaction, A gives B. Same reaction I'm writing again, right? The reaction is of the order 1. The order of reaction is 1. The order of reaction. First, it's a first order reaction, right? Let's say at time t is equal to 0, the concentration of reactant right now is 100 molar. At time t is equal to 0, the concentration of reactant right now is, for example, 500 molar. It is 500 molar. Let's assume 10% of the reaction is completed in 20 seconds. Let's assume 10% of this reaction is getting completed in 20 seconds. Since we know time taken to complete a certain percentage of a first order reaction is independent of the initial concentration, so I must say time taken to complete same 10% of the reaction over here will be again 20 seconds, right? Time taken to complete a certain percentage of a first order reaction that's independent of the initial concentration. So no matter what you are going to keep the initial concentration, time taken to complete a certain percentage of a first order reaction, it does not depend on the initial concentration of reactants. Yeah, as simple as that. So time taken to complete, for example, 10% of this reaction when the initial concentration was 100 molar is 20 seconds. Therefore, time taken to complete same 10% of the reaction when the initial concentration was taken as 500 moles, it's again going to be 20 seconds only, because I told you time taken to complete X%, time taken to complete a certain percentage of a first order reaction that's actually independent on the initial concentration of reactants. Okay, I'm sure it's clear to you why I gave you this statement. There was a question asked in your JEE once from the same concept. This was the question. I'm sure you all are going to kill this question now. Yeah, see guys, look at the question carefully. The catalytic decomposition of the reactant over gold is a first order reaction. Let's say the reaction is something like this. A gives B. It's a first order reaction. It's a first order reaction. It's mentioned in the question. Yeah. When the initial concentration was 200 molar, it was 73% decomposed in 100 minutes. That means 73% of this reaction was getting completed in 100 minutes. Okay. Now, when the initial concentration is, in the same reaction, when the initial concentration is kept as 600 molar, in 100 minutes, what is the percentage of reactants getting converted into the products? What is the percentage of reaction to get completed over here? Okay, what percentage of reaction would have got completed right now? See, I'm not changing the reaction. It is just I'm changing the initial concentration of reactants. 73% of this reaction was completed in 100 minutes. So again, in 100 minutes, only 73% of the reaction will be getting completed because it's independent of the initial concentration of reactants. So answer of this question is simply going to be 73%. No need to do any sort of calculation over here in this question if you know the concept. Yeah. Right, Arsalan, I did not teach the coordination chemistry yet. Most probably I'll be doing that in the next week. Let me know in the chat box first. Is it clear to everyone? Yeah. Is it clear to everyone? Give me some green signal from the chat box so that I can move on to the new thing. Let me know fast, let me know fast. Perfect, guys, wonderful. So let's move on and let's talk about a few more interesting things, okay? Perfect. This is a statement which I've mentioned over here. Time taken to complete 75% of the first order reaction. Simple? It's very simple now. I'm sure it's very simple. Understand, how will I be solving it? Few minutes back, I gave you a relation. Time taken to complete X% of the first order reaction, it's equal to 2.303, or let's not use this. Let's use the general procedure. Let's use the general procedure. For example, the first order reaction is A gives B, whose rate constant is K, right? Order of reaction is 1. Yes. At time t is equal to 0, the initial concentration of reactant is A0, the initial concentration of product is 0. Now, I'm assuming 75% of the reaction is getting completed. So when 75% of the reaction will be getting completed, at that time, 25% of the reactant will be still left in the container, right? If the initial concentration of reactant was A0, so at T 75%, I'll say 25% of A0 will be still left in the container. So which is equal to 25% of A0 means A0 divided by 4. Okay. If I use the integrated rate equation, we know T is equal to, or I'll be writing T 75% will be equal to 1 divided by K. It's going to be ln of A0 divided by AT. What is the value of AT? Value of AT right here is A0 divided by 4, right? Just a second. Yeah. Value of AT right now is going to be A0 divided by 4. As simple as that, okay? Yes. So A0 got cancelled. So I'll be getting K is equal to 1 divided by T 75%. Okay. It's going to be ln of 4. Ln of 4 you can write as ln of 2 square, which is going to be 2 ln 2. 2 ln 2, like this. Yeah. Right. Let's call this as equation number 1. Let's call this as equation number 1. Few minutes back, we derived the half-life for the first order reaction. I can say half-life of the first order reaction, which is represented by T 1 by 2 or T 50%, that's equal to ln of 2 divided by K. This is something which we know, right? People, if I divide these two equations, this is equation number 2, for example, this is equation number 1, for example, right? This is equation number 1. If I divide these two equations, what I'll be getting? What I'll be getting? Okay, if I divide these two equations, I'll be getting something like this. Time taken to complete 75% of the first order reaction is equal to 2 times the half-life of the first order reaction. Okay, this statement is only valid for the first order reaction, right? So remember, from now onwards, 75% of the first order reaction is actually getting completed in 2 half-lives. Okay, 75% of the first order reaction is actually getting completed in 2 half-lives. Yeah. Similarly, there is one more result for the first order reaction, that is 87.5% of the reaction gets completed in 3 half-lives, right? And remember, 99.9% of the first order reaction, it gets completed in the 10 half-lives. So remember these 3 points as well. These are very, very important because, I mean, there are some questions in which directly you can use these results and get your answers. Yeah, I'm sure these will be clear to you, right? Exactly. This is something which we have done. So people, this was all from my side in the tonight's discussion. We just started the first order reaction. I did not finish the first order reactions yet. Okay, I'm going to continue the first order reactions in the next session. Yeah. So I'm sure you would have enjoyed the session till here, right? And the ones who have not joined into the pro subscription into the actual Vedantu classroom, do get enrolled as soon as possible because the batch is starting, right? These are the plans which you can take, any one of the plan, whatever you're comfortable with, right? You can take any one of these plans, or if you're new to Vedantu, you have no idea of how the actual Vedantu classrooms look like, how the actual Vedantu platform looks like, you can take these plans for a month. Okay, you can take them for a month, any one of these plans. The choice is all yours, right? Give it a try. If you think you are getting benefited, then go for the actual pro subscription plan. This is the pro subscription plan for the light for 12 months. Okay, this is 1 year package over here. This is again 1 year package. This is again 1 year package. The choice is all yours, whichever plan you want to take. And no need to pay entire amount in one go. You can pay the amount in EMIs as well, in installments as well, right? And there's a link in the description box of the video if you want to get enrolled, right? Link is there in the description box of the video. Click on the link. Use the coupon code WSPRO while enrolling. So after using that code, you'll be getting some 20-30% off as well. Yeah. And there is one more link in the description box. That's for the Telegram. Do click on the Telegram link. Get added to the Telegram group and stay updated about the classes. And at the end, the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well, right? Do like the video, share the video, and do not forget to subscribe to the channel as well. It was nice meeting you. I'll see you guys tomorrow at the same time. Till then, you guys take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye.